Hi. My name is Bo Pang. I am presenting the paper, Unsupervised 3D Point Cloud Representation Learning by Triangle Constrained Contrast for Autonomous Driving. We aim to provide a unified unsupervised representation learning method for autonomous driving that takes all the sensors of different modalities and both spacetime dimensions into account. But pixel point level multimodality contrastive pair across time sequence is difficult to obtain. Thus, we need an automatic method to solve this and design a discriminative contrastive framework. The core design is the triangle consistent constraint, which forces the 3D point features to random walk across the temperature dimension and modality dimension, and get back to itself to learn representations. With the proposed Tri-CC pre-training method, we obtain effective 3D LiDAR representations that perform SOTA on 3D segmentation and detection. The starting point of this work is to learn general unsupervised 3D representations with the help of all available information in autonomous driving scenarios. This requires us to have a dense unsupervised algorithm that can integrate multimodal information and temporal information under a unified framework. We follow the discriminative unsupervised framework, specifically the contrastive learning framework. However, it is very difficult to obtain multimodal dense positive pairs in time sequence, so our core problem is to find an unsupervised solution that can automatically discover positive pairs. To get the dense positive pairs across multimodality and the temporal dimension, we design the cycle consistent constraint to automatically dig them. The cycle consistency requires every pixel or point in the first feature map to travel through all the maps and get back to the map of itself. The travel process between two feature maps is formulated as a similarity transition matrix as the first equation shows, and we adopt the cosine similarity as our similarity function. By linking all the transition matrices of adjacent features and connecting the tail and head, we can form a cycle as the second equation shows. And each row of this multi-step transition matrix represents the probability of one pixel transferring back to every pixel in its own feature map. With the final transition matrix, we optimize it by forcing every pixel to cycle back to the same pixel with the highest probability, since this kind of feature map has better discrimination. And in our auto-driving scene, the feature map groups consist of three components: the camera feature of frame T, the LiDAR feature of frame T+1, and the LiDAR feature of frame T. The cycle contains three paths as the figure shows, thus. We call our method the triangle consistent constraint. And in practice, we can easily obtain the mapping relations between the camera feature and LiDAR feature of frame T by the calibrated camera and LiDAR pose. Thus, we adopt a fixed off-the-shelf transition matrix between them, instead of the random walk. With the automatically found positive pairs among the three feature maps, we can conduct contrastive learning between each two of them. The first equation takes CT and PT+1 as an example. We can see that the positive pair is determined by the transition matrix learned from the previous step. Since the transition matrix is originally a similarity probability matrix, we can directly utilize the most similar counterpart as the positive partner. And the total contrastive loss is the sum of contrastive losses between each two of the feature maps. We follow the current mainstream discriminative unsupervised learning structure to build our networks and the training pipeline. The learning network is composed of a 2D backbone, a 3D point cloud backbone, and their projection heads for consistent constraint and contrast. The projection heads are simple MLP to assist the representation learning as the mainstream methods do, and they are removed from the backbones in downstream transferring. All the inputs are augmented by a group of transformations, and the outputs of the projection heads attached on the backbones are the feature maps we adopt in losses. In experiments, first, we conduct the linear protocol and fine-tune protocol on 3D semantic segmentation task on new scenes dataset. We can see that our Tri-CC on UNet achieves much better performances and pushes the SOTA fine-tuning results by 1.0 mean IOU. And its learning efficiency is much higher too, since TriCC pre-trained for 20 epochs surpasses all the baselines pre-trained for 50 epochs, a large gap. For few-shot fine-tuning under the 1% fine-tuning setting, TriCC on UNet improves 10.9 mean IOU than the random initialization setting, 3.0 mean IOU better than the previous SOTA results. We also transfer the pre-trained representation on 3D detection task. It is seen that TriCC provides a 2.5 MAP and 2.7 MAP performance boost over the random initialization for second and PVR-CNN models. Here we provide more experiment results for your convenience. We claim that our TriCC can automatically find high-quality positive pairs. Here we show some visualization of the dense matching quality. We pick a pixel from the input image and show the similarity heat maps of all the point cloud points in the current and next keyframe. This is a human example. We can see that the target pixel is successfully matched to 3D points with the human semantics. This is a car example. Also, all the cars on the road are successfully matched. This matching is not a one-to-one predefined matching, instead, almost all the positives are dug out. That's all. Thanks for listening.